just mute out during recording?
No, you're good. Okay. Hi, everybody. You're missing an awesome class today. Okay. I have your test thermo and gases graded. I graded a lot this weekend. I'll give you back. One person still hasn't taken thermo, so I can't give it back to you, but I can tell you your grade. And then the gases, I just have to put together the free response and multiple choice, the grade, so I can tell you that. So come get that later. Is anybody on this list? Yes. Tyler, see me. Okay. And then I used to do corrections on their test after every test, and I would use it as a quiz grade. But quizzes are worth like very little in this class. So what I'm going to do is, instead of you correcting every test, choose your 3 worst tests, and I'll give you your folder back with all your tests in it. You're only going to be correcting the free response. So if you totally just omitted a question or you got it entirely wrong, redo it. If you made like a calculation error, you forgot units, just something really minor, just correct that. Okay, so that your 3 worst tests, I'll give you back all of them in a folder tomorrow. You need to give that to me by December the 3rd. I put that on here someplace, right there. Okay, so you'll be taking them home. Compare each other, use each other. Don't let people tell you no. Find some people that will work with you. Okay. What else on here? Yeah, only free response, not multiple choice. Absolutely not multiple choice. And I think some people are going to be gone Wednesday or Friday for UNCC trip. Anybody? English? Yay, okay. And then for gases, I'll go over some of these when people are back, but like these are the gas free response questions, which is a take-home test, which should have been fantastic. Most people's were. But if it asks you to, like, to say something about a theory, like, actually say something about the theory. So, like, the kinetic molecular theory, that first question, some people mentioned it, some people just didn't even write it. So, when it specifies to do so, do so. And then units, we got to make sure we put our units on everything. And then, deviation. Remember the 2 things that vary deviation, or that cause gases to deviate from ideal gas behavior?
Oh, like
Intermolecular forces were the biggest thing. So, like, if you can determine the IMF of a particle, and it's a strong IMF, like hydrogen bonding, it's definitely going to deviate from ideal gases because there's going to be less bouncing around, so less collisions, therefore less pressure. The other one is just size. If you're trying to compare everything based on size, the larger ones will take up some of the volume, therefore decreasing the volume available. Okay, so we'll talk about that more. We'll do thermo later because I have one person that's taking tests and I don't want to help them. Okay. I am going to do, that graphing worksheet, it had like determining order based on graphs and data tables. Initially, I was going to tell you guys to do that last week, and then I took it off the homework so you guys didn't have to do it because I had integrated stuff in it and I didn't even want you to touch it yet. So I'm going to do that worksheet with you next week. Okay, so that's why it says, I have this crossed out. That says inlet. So the people presenting for this week, integrated rate loss, which is tonight's homework, Lauren, who's not here, Austin, who's not here, kinetics, review 1 and 2, Nathan and Molly, so you guys will split up. Because it's a big question, you guys will split that up, and then these next 2 people will split that other one up. FRQs, this you'll just see it on the look for the homework, and just the next day you'll do it. It's not until next week though. Mechanism practice is this week for Austin. FRQs will be presented next Monday and Tuesday, so neither of you guys. And then multiple choice, I didn't put the numbers here, but I'll tell you, Tyler and Lexi, those numbers. I gotta look at them on my paper. I don't know why I didn't put them, and that's online. Okay, Crystal Violet. Let's go. Pull it up for you and ask you questions. So I know the one about the before, during, after. Can I go ahead and do that one?
Yeah.
Okay. Number 4 on the pre-lab. So, like, on the very first thing was you had to know the BCE for this reaction. So essentially, what you're doing is you're going to be reacting crystal violet, which is what color?
Purple.
Purple, violet. Okay. So you're reacting crystal violet, which is violet, and sodium hydroxide, which in the NIE is just OH minus. And this crystal violet actually has a plus on it. It's a big, humongous molecule, but it's a cation. And then it reacts to form CVOH. Okay, so when that plus is negated with the negative of the OH, it's going to be neutral, right? But also, it takes away the ability for it to emit color, so it's colorless. So in the lab, you have to use something that's going to track color changes. What are you going to use?
An indicator?
What tool? What big machine tool?
Oh, the spectrum.
Right. So you're gonna use spec 20s, which are a little more complicated. You got to know the wavelength. Then you're gonna clean up the cuvettes, fingerprints, and all that junk, and measure the wavelength put out, the absorbance or the transmittance, whatever. We can use those, or you can use colorimeters, not calorimeters.
I thought it was a color.
Color emitter. It measures. It's a thing that measures color. And what it is a little device you hook up to the computer. It's a Vernier product. It's like a probe, like a temperature probe or pH probe, but we're using colorimeters. They only go to 4 wavelengths though, so whatever you got for your wavelength on number 1, where you had to look at the graph until the peak, you'll choose the wavelength that's approximately that, because there's only 4 to choose from. For Spec 20 has like every wavelength, and colorimeters have 4. So like I think there's one that's like 565 nanometers, and that's probably the one you'll be using. I like these because they go straight to the computer and puts it in the calculations for me. I don't even have to type anything.
We could just use which one we use.
So I'll let you choose.
It's like a certain amount of age.
There's plenty for everybody to use which is perfect. Okay, so choose what you want. Okay, so that's why you have to use, I mean, we're tracking color changes, which is essentially tracking what changes. The color's degrading or declining, what's also changing?
The amount of reactive.
The reactant. So we're truly in for rates, we're tracking the concentration of reactant. So as the color decreases, what also is going to be red that decreases? Okay, the concentration of CV, because the absorbance, right? So we're tracking color based on the absorbance. So it's the amount of light that transferred through a pipe. I woke up at like 3 o'clock this morning. A cuvette, thank you. So the absorbance goes down because the color's going down, which means the concentration is going down. So we can track that over time. We can figure out the rate law. Okay, we're going to integrate it with time today. Anyway, so back over here. CV plus OH minus yields to products. I don't really care what the products are. My first question said, what if you were given a 1-to-1 ratio of CV versus OH? So that means 1-to-1 means kind of like 1 mole, 1 mole. I like to use moles because it's easier. So 1 mole versus 1 mole. What happens in this before, during, and after? What's their ratio of the reactants? 1-to-1. So they both run out at the same time, right? So they're both LR, limiting reagents, so they're both going to run out at the same time. You're not going to know who is actually controlling the rate of the production of the product. They both run out at the same time. You have no idea who's controlling that rate. Okay, so it's harder to determine rate laws when you run out of both reactants at the same time. So if you have one in excess, it allows you to kind of focus on the one that's changing the most. So in the next case, this was the 1-for-1 law. The next one said like 1,000-to-1, where you had CV plus OH yields CVOH, where you had like 1,000 moles of sodium hydroxide and only 1 mole of crystal violet. So who's the LR here? Crystal violet, right? So you're minusing 1 mole here, you're minusing 1 mole here. You're left with 0 of this and 999 moles of the hydroxide, which means that when you compare the amount used, you use all the crystal violet, but you're only using a small percentage of the sodium hydroxide. So if you have left over 999 and you started with 1,000, what's your percentage used? I mean, sorry, your percent. Okay, your percent used is like 0.1%. You still have 99% of what you started with. Okay, so that's essentially staying the same. Yeah, I mean you're really close to the same. So we're going to call that the concentration change of OH minus. It's pretty much not changing. We're going to say it's a constant because it's so close to the original was. So this one kind of helps you with number 4 because we're going to say that we're not really going to be focusing on the amount of OH change because it's not really changing that much. So when we break it down and we use this knowledge in number 6, I think it was, which was how do you get from equation, it was like rate times K, concentration of CV, times concentration of OH. How do you get from here, that was equation 2, I think, to equation 4, K prime CV. I think that's what it said. How do you get from here to here? What have I done? See, you say it's to 0 order, but what I'm going to say is that this K has changed, right? So I've made a K a new constant. What did I lump together?
You lumped the constant concentration of OH with the constant K.
Yes, so who cares what K is? K is a constant. If I pull 2 constants together, I make K prime, which is just going to be a simplified version of the rate law. Okay, so that's why it says in the lab, if you're reading, it says find the pseudo rate law constant, because pseudo means fake, right? So this is the fake rate law constant, but it makes our math a heck of a lot easier. So we're only focusing on the changing concentration of crystal violet, because that's the only thing we can track, right? That's the only thing that's colored. I can't track the concentration change of OH because it's clear and it looks the same from beginning to end. So I have to track concentration of crystal violet. change, which will do the colorimeter spec, and then you're going to solve for this K prime, which is just it's like K star in your lab, but it's called K prime. So we're going to solve for that. And then on the lab it says, let me get the version online. It says you're going to write a lab report on this. I do not want you to write another lab report. You've written enough for now. We're going to kind of do every other unit. So instead of doing that, you're going to do a public service announcement for kinetics. So some interesting part of kinetics in the real world that you would like for people to know about. So, I mean, the scenario given to you in the beginning of this lab is like an ecological situation where you have a pesticide and you want it to degrade every so often so that you don't have pesticide building up in the environment. There's a list that's online that some people have already chosen and put their topics up there, but you guys can choose any topic you're interested in. Someone I think from this group put the kinetics of popping popcorn. That's a very important thing that people need to know, right? Huh? Yeah? Okay. So make sure that you choose something you're interested in. You're going to talk about the kinetics of the reaction, talk about the importance for people around the school to see, and then have some like images on it. The information's online. Okay, so versus the lab report poster. Cool. Okay. Questions anymore on this one? All right, let me know, because the lab I pushed back to Thursday, and the iodination of acetone lab is Friday, so I flipped them. So we're doing the crystal bottle one first. Just make sure you have your procedure. Procedure very well may be like 5 steps. Okay, it's going to be a very short procedure, because if you do one trial and you get good results, I'm not going to make you do it again. The procedure for this will be very short, so you know, upload it by Wednesday at 9.
Do we still do the pre-lab for the other lab tonight?
No, I changed that on the homework.
Okay.
Yeah, I've rearranged it because I pushed our test back a day. Test is next Wednesday. Okay, just because I didn't want people to feel stressed, because kinetics is kind of stressful.
So most people think that test is not this week, not next week, but right before Thanksgiving.
Okay, so hold off on any more crystal ball stuff. Let's jump into integrated rate laws. This is just a bit of stuff that I need to make sure that you're aware of. If you want to write it down, you can. The one thing I want to make sure we know is our log rules. These are from Algebra 2. You remember these? All right, make sure you know this, because we're going to use this a lot today. The other stuff is pretty easy. You'll notice that kinetics starts to kind of become a little bit more cumulative. We just did it before, during, and after, which is, basic stoichiometry. You're going to be doing prediction of products a little bit. You're going to be doing some molarity stuff. So some of that math background. There's a little bit of thermodynamics we'll get into at the end. So there's a accumulation of everything we've learned so far coming into kinetics. Remember, your rate laws are always positive. That's important. I'm going to teach you a little bit more about using graphs, so just wait for me on that one. But graphs can be used to determine rates, not only data, but graphs. So the AP exam takes pride in like giving you images and graphs and tables. They really want you to know how to use anything given to you to determine what they need to know. Ooh, yeah, we'll get into reversible reactions a lot more when we get to equilibrium, but you might find that you'll come into some problems that say you use up all the reactants, but then it's a reversible reaction. So the products react to go back to reactants again. So it's just called reversible. You'll come into one question like that. Let's see here. Oh, the rate reactants. I just want to verify that. We all know that again. Rate laws are only dependent on the reactants. That's it. Don't put any products in there. And the K is a constant, because whenever, like I always tell us to use trial 1, when we go back after we find the rate law and we plug it in and we solve for K. But if you use trial 2, it'll be just a tiny bit different. If you trial 3, it'll be a tiny bit different, because when you're changing the concentrations and it's not 100% linear in the relation, sometimes the K constant changes just a little bit, but most of the time it's fairly constant. So some of us might get a tiny bit different answers, but it will still be close. So this is the most important. The main one is if we are, for minusing 2 natural logs, you can pull them together as a fraction for the denominator, or numerator over denominator. Alright, let me know if I talk too much. Integrated means integrate with time. That's all this means. So what you're going to do is you're going to say, okay, I have concentration of something. You're going to see how the concentration changes over a certain time. And what else I want to tell you here? You actually can do this right now from the rate laws you already know. So like rate equals, you remember this one? Rate equals like negative change in concentration of a reactant over change in time. Remember that from a graph, like the concentration of reactants are going down, so it's a negative. So you put the negative in the front to offset it, so it's a positive rate. We can go directly from here to these new equations we're going to write with time right now if you know calculus. If you don't know calculus, let me show you how to do it. You're not going to have to do this, like go from this rate to the integrated rate by yourself. Most people memorize what the integrated rate laws are. And the AP exam gives you two of them on your reference sheet. So they understand that not everyone's taking calculus, so they don't cover that. The thing we will have to do is to take the integrated rate law and get to the half-life equation. It's all foreign to us right now, but you'll get to it. Okay, other than that, so if you know the rate law, the differential rate law, you can go directly to the integrated if you know how to do the math. Other than that, though, we're only focusing on one reactant because this is the easiest way to do it is in the reference to one reactant. That's why in this Crystal Violet lab, we're going to put so much excess sodium hydroxide in it, it allows us to focus on one reactant. Otherwise, it's way more complicated. We're not there yet. We're not going to get there. This is Chem 1 in college. Okay, other than that, this is also experimentally driven. You have to have data. You can't just think of it and go with it. You have to have data. Let's do some. Okay, so do not write all this down. We already know this. Concentration of the reactant doubles if it's first order, which will cause the rate to double. We know this. I'm going to show you how to get from here to here. This one you probably want to write down. That is called if I ever tell you to write out the integrated first order rate law, that's what it looks like. Natural log of A final, so this is like the final concentration, that's what the little F means, equals to the negative K, what's K? Rate law constant, right? Times time, so little t represents time, plus ln of A initial. So A naught, you can also write that as concentration I, like that. Same thing. So now we're going to be talking about changes over time, where you have to have an initial concentration, you have to have a final concentration. And you'll get that from a graph, you get that from data tables, you can read it on Spectronics. All right, so, okay, what mathematical formula does this kind of resemble? Think abstractly. Something equals something times something plus something. What's that called?
Y equals mx.
Y equals mx plus b. Okay, that's what I wanted you to see, because if you can rearrange integrated rate laws in the y equals mx plus b formula, and then you graph them, and they are 100% linear. They're you know the r squared value you had to do on your stat plot calculator? If the r squared value is very, very, very close to 1, that means it's very linear. So that means that this relationship exists, and that rate, whatever we're talking about, is first order in this case. So like second order has a different y equals mx plus b. Zero order has a different y equals mx plus b. So what you'll do is you'll graph each of them. Whichever one is the most linear is the order of that reaction. Okay, so you're going to be doing a lot of stat plot stuff. Okay. All right. So what is this one going to look like? Which one? What's the x-axis here? What's x? Time. What's the y-axis? ln of the concentration, right? Because this is actually the entire y over here. So when you graph it, though, is it positive or negative slope? Negative. So it should look like that. That's what it should look like when you graph it. Okay, so that's what this says here. Plot of ln of A versus time yields a straight line. If it does yield a straight line, then that is the order of that reaction. We're also going to calculate half-life. All right, so example, carbon-14 dating. Whenever you figure out how much carbon-14 is present in a rock and you compare it to how much carbon-12 is in a rock, you can take the concentration changes and determine the half-life. Every single time we've said half-life, we've been talking about first-order half-life. There are 3 half-lives, right? Okay, so radioactive decay, it doesn't matter if I have a kilogram of carbon-14 or 1 gram of carbon-14. Its half-life is going to be like, I think it's like 120,000 years. It doesn't matter how much you have. So this is independent of the concentration. It only depends on the rate law constant. It just depends on what type of reaction, what the reaction is we're talking about. I'm going to show you how to get here though. Cool? Can we go? All right, do not be scared. I have a bunch of calculus to show you. Okay. All right, so from the back of a calculus textbook, you go to this integral table, and you say, okay, this little swoopy thing here is an integral, for those of you who have not taken it. I really like calculus, but I don't remember everything, so Shanna, correct me if I'm wrong. Okay. I had a great teacher. I was like, I'll take calculus EF with you, if there was one. Okay, so 1 over x, What's that say?
We just need
dx. So that means something though.
derivative of x.
Derivative of x. Okay. So that equals ln of x. This is a law. This is given to you. Do not, don't try to think through it. Whenever you have a constant and you do the integral of it, the constant, times d of t, the constant times time is going to remain. Pretend I know what that means. Okay. So we know how to write this. Yes. We also know that for first order, A equals that, because that's the differential rate laws. When I rearrange this, so I have, I just switched these, divided by A and then times by delta t, I get the stuff in red right here. You see what I did? I just switched these two values here. So I have K times delta t over here, and A minus the change in A over A. These are all concentrations. Okay, now the reason I did this is because I needed to be able to use these rules, so I had to have some K times delta t, which would allow me to equate it to K times t, which I'll do right here. So I got from here to here easily. The other one though, with integrals, it's always integrated per time or some change. So what you do is you have to go from some point to another point. So on the integral, sometimes you'll see like A final and A initial here, but we never do like initial minus final, right? Ever. We always do final minus initial. So when we do this integral, you're going to say whatever this is equals ln of x. Okay, but we have to go from point A to point B, which would be A final minus A initial. Now, where did I get this negative from? Here. Yeah, this negative stays as is. It's going to get pulled out. Okay, so we've integrated now. Yay, we're done with the calculus part. It's not as bad as it looks, right? Okay, but now I'm rearranging this because I want this to end up looking like y equals mx plus b. So I distributed the negatives throughout. Now what do? I divided by negative. Divided by negative, so I got negative kt over here. And then what did I do to get here? I added the ln of the A initial to the right side. So now this looks like y equals mx plus b. You just had to integrate it. This is what it's called integrated rate laws. Okay, so once I'm here, I can see the parts that I need. I see that this is the y-axis. I see this is the slope. I see this is the x-axis, and this is the y-intercept. When I graph it like I did earlier, that's what it looks like over there. If it is very, very, very close to 1 when you get your r-squared value, then it would be, whatever the reaction it was, it would be first order. And so that's where I get my slope. If I ever ask you to say, if I say, what's the rate constant for something like this, do not calculate the rate constant. Look at your graph and tell me the slope, and that's it. People take forever to try to calculate it. You don't have to. If you have something that's linear and you have some information in your calculator that can give you the slope, just use it. Pull it off graph. All right, so this is the part you're not going to have to integrate, but I just wanted to show you because versus me just saying it's accept it, agree to disagree, I'd rather show you. All right, but this part right here, you may or may not have to do by yourself on the AP exam. Okay, so what's the definition of half-life? Okay, so I'm going to go from A initial to half of A initial, right? So instead of putting A final right here, instead of putting A final right there, I'm going to call that A initial over 2. So it's just half the initial amount. And instead of calling TT, I'm going to call it T1 half to specify I'm solving for half-life time. So at half-life, A initial over 2 is equal to A final. So I'm just going to plug that in and go with it. So when I plug that in, this is what I get. ln of A naught over 2 is equal to negative KT1 half, just designating our half-life time, plus A initial. See what I did? Yeah? All right, now I want to solve for the half-life, so what am I going to solve for? What variable? K would be my rate constant. I want to solve for T, to be my half-life, right? I want to solve for T. So how do I solve for T? Isolate it.
Subtract.
Mm-hmm.
The natural log A.
And
then divide by negative
oops, yeah, that's right. I just started to divide on the side. Minus ln of A naught, that's 2 right there, and then divide by K. Right, so there's that, me minusing, and then here's, what did I do? Oh, I want my T to be a positive number, so I divided by negative to get the negatives distributed, and then I finally someplace here, I'm going to solve for k. Solve for t. Oh, okay. So back to your log rules right here. When you have ln of something minus ln of something, rearrange that so you have ln of that first thing divided by that second thing. So you're just transferring based on your log rules. So I've written this here really, really sloppy. So this is just ln of a naught over ln of a naught over 2. But some of us don't see very well, I'm racist, some of us don't see very well how to combine two humongous fractions. So if you write a naught over 1 and then a naught over 2, when you combine the outsides, I can't remember what someone called that last week, but combine
Copy dot plot.
what's it called?
Copy dot plot.
Copy.
Because you copy the first fraction and then you do the multiplication symbol and then you flip it.
Okay, I'm gonna call that rearranging the fractions. Okay, so then you get a naught times 2 over the middle stuff, which is just a naught times 1. What cancels out? A naught, right? So only leaving you with ln of 2. That's it. Okay, so once all this mess is gone, you get ln of 2 equals to k t 1/2. Then how do you solve for t? Divide by k. So,
oh, it's 1/2 a subscript.
yeah, I'm sorry, 1/2 is a subscript. So divide by k. Remember that ln of 2 is equal to 0.693. Just remember it. It's going to be easy instead of putting your calculator all the time. Or sometimes on multiple choice, they might say, solve for t. And they'll give you really basic information, like really easy math. But if you have to go ln of 2 in your head, go, what's ln of 2? Nobody knows that. But if you know it this way, you can do the math easier.
So you're saying that all that away in the notes.
Yes, but if you can't remember that, you can do it again. You can do this. All we did was plug in that a over 1/2, and that was it. And then we just isolated for t. So if you don't remember it, then know how to get there, and this is the how to get there part. So t 1/2 equals to 0.693, I can't talk, over k. What do you notice there's not in here? Concentration. So radioactive half-life has absolutely nothing to do with the initial concentration present. It's just based on that particular reaction. So it's always going to be the same, doesn't matter how much you have. That's why this is important to know. And then you can integrate it. You can also get this information from a graph. So if you have your concentration initial and you want to figure out what the half-life is, you just go to a point where it's half that concentration, whatever it is, and you find the time associated with that. The time it went from here to here. That would be the half-life. So from a graph, you could also get half-life as long as it was concentration versus time, which most rates are, if they give you data. Cool?
So they always just give you k.
No, you would solve for k and then plug it into half-life. Yeah, you would probably solve for k first. Or they could give it to you. All right, second order. We know this. Doubling it causes the rate to quadruple. We know this, and now we're going to integrate it. Yay! Same thing. Y equals mx plus b. So what is our y-axis in this case? What's the label for the y-axis in this case? Huh?
So concentrate 1 over.
Yeah, sorry, hold on. 1 over concentration, right? And then on the bottom is always time. So time is the what variable? Independent or dependent? Independent. Time, concentration is changing as time changes. So time is independent. Positive or negative slope? Positive. Because of this positive k value right there. All right, so I'm going to show you how to get there. Anything else here? Just did that. And then half-life, I'll show you how to solve for that. And then the importance of it when we get there. Cleo? Can we go? All right, so no scary stuff again. Here's our integrated rules. When you have d of x over x squared, so this is x squared because we're doing second order, which is to the second power, so I need something with squared in it. That'll give you negative 1 over x. So when we solve for this integration, we're going to have a negative 1 over whatever we're integrating. Okay, so rate law, same thing, but in this case, for second order, equals to the squared value. So I'm rearranging this so I can integrate it. Because I have to have the k and the delta t together, because that's how I'm going to get the kt in the end for integrated rate law. So when I rearrange this, all I did was flip the a squared and the t, delta t right here. So divided by this and times by that. So I got to here and here. I probably should be right on the board. People can't see where I'm putting me. Okay, so I got here, and then I'm going to integrate it in reference to a naught to a final right there, but using the rule for integration. I think I got green. Okay. So when I integrate with that rule, this over a squared will give us negative 1 over a. So negative 1 over a right here. But since this is going from a initial to a final, I need to write it in a way so I have final minus initial. So minus a negative 1 over a naught. Just trying to do that for the benefit of my videoers. Okay. So this negative stays out front because that negative there, and then kt is kt. Alright, so I've almost done, I am done integrating, I just need to rearrange now. Rearrange so it looks linear. So the first thing I did was distribute the negative, and then when I distributed the negative, I had to switch two values because it was like a negative out front. I had to switch two values to get the negative out front because I need to add that 1 over a naught to the right side so that I have a final equals kt plus 1 over a. So when I rearrange it, it looks like the law that I initially told you. So I'm just proving to you how we got there. So you can go through each individual step. I tried to lump some of those steps together. Alright, so y equals mx plus b. When you look at your slope, it's positive because the k is positive number here. And then you have your y-axis, which is probably the most important thing there. If you put the information for this, for like a data, if I gave you a bunch of data in a data table, you put in a calculator, you did your stat plot, you did your lint reg, and then you found your R-squared value is really close to 1, then it would be, whatever the reaction was, it would be second order. Okay, so now this part up here would be, this I think is the one given to you in your reference sheet, I believe. Okay, but now we want to do the half-life. That's where this pink part is. Okay, so what am I going to do again for my A final? Plug in what?
Okay. A initial divided by 2.
Right, A initial divided by 2. It's the time it takes for A initial to go to half of what it originally was. So I'm just going to plug that in again, but into this formula. So I'm taking this, setting them equal, plugging this in to the formula for second order integrated rate law. So that means A over 2 goes into this denominator right here. So it's going to look a little bit weird. It's going to be a bunch of fractions floating around. So it's way down here. Okay, so when I plugged it in, I've modified my fraction so it was easier to work with. So instead of just putting 1, I put 1 over 1 here, and then a naught over 2 equals to k t1/2, which is just the half-life time, and then plus 1 over a initial. So when I rearrange this, 1 times 2, 2 goes on top, right? And then 1 times that goes on the bottom. So essentially this equals to that right side of the equation, which gives you this, and then guess what? We minus 1 over a. So I did it like this time. So minus 1 over a on this side, and then this is easy because the denominator is the same. If the denominator is the same, 2 minus 1 is just 1, right? So 1 over a equals k times t. Solve for t, you divide by k. But since this is already a fraction right here, when you divide by k, k just goes into the denominator. So this is what you need to know. Some people like to memorize. I just want to give you that option. If you want to memorize, you can. If you want to go through and do it, solve for it yourself, you have the ability to. You're smart enough to do it, you know? You can know the math skills. So this one tells you that the concentration is important, right? So is the half-life constant? No, the half-life for whatever this rate is changes every single time you change the initial concentration. So it's very, very much dependent on the concentration. These are very, very rare because I can't say, oh, the half-life of this reaction is 120 years. It's going to be, well, what concentration are you talking about? But these are rare to see because these are a lot more complex and there's too many criteria that have to be met. So at each successive concentration, the half-life is 2 times as long. So the half-life is short, then it gets longer, then it gets longer, then it gets longer. And so if you were trying to predict how long something stayed in the environment, if it was a pesticide and it was second order reaction, it would take you forever to figure it out because the half-life changes every single time you change concentration. So these are harder and they're very rare. Alright, one more. Yes. Zero order. Okay, we know zero order is rate is equal to k. That's it. Because if it's a to the 0 we can reduce that down to 1, so rate is equal to k. So this one's a lot easier, because the variables are very far and few between. Few and far between. So I'm going to show you to get from here to here. The only thing that's different about this one is, since I can't like speed up a reaction by just pumping some more concentration, some more reactants in it, because obviously look, the rate has nothing to do with the amount of concentration at all, or amount of reactants at all. So I can't speed up that reaction by putting more reactants in it. How do I speed up the concentration? I mean, the rate. I can heat it, or I can add a catalyst. So most of the time, these are going to take place with a catalyst. So like a catalytic converter in your car, I think it converts carbon monoxide. It converts some gases to other gases that are not so bad for the environment, which is a good thing. It's a zero order reaction in your catalytic converter. What's a catalytic converter have in it? Catalyst. Okay, there's like platinum and some other stuff in there. Platinum's a really good catalyst. So that's going to be something like, you know, environmentally friendly that could be good to talk about. What was the other one I was going to tell you about? Oh, your body. Your body has tons of catalysts, which a lot of the stuff that happens in our body can be considered coupled reactions, which we'll get into, and then zero order reactions. Because it doesn't matter how much is there, it just depends that it's going to happen. So you have to have a catalyst. Metabolism has got a lot. It depends on when you eat, your genetics. It's got a lot of stuff. But yeah, your enzymes speed up your metabolism. And let's go. Okay. So that one looks easy enough, right? This stuff that we already knew from like basic rates equals to k, because that's our zero order. This one we're going to rearrange that what did I do? No, I didn't rearrange it. Did I rearrange? No, I didn't. Okay. Yeah, I did here. I was like, I knew I did. I brought that t, delta t, over to the k side so that I could do integral of k delta t. Integral of k delta t is just equal to kt. That's that constant I told you in the integrated first rate. And then the integral of this is just a final minus a initial. There it is right there. So a final minus a initial, these are concentrations of course, equals to the negative, so that negative stays with us for that constant kt. I didn't graph this one on the previous slide, but I graphed it here. Okay, so whenever you're looking at y equals mx plus b, once I get down there, sorry, let me rearrange. All you do is add your a naught here, and then add your a naught here. So you get y equals mx plus b, where you have a final equals negative kt plus a naught. The y-axis is concentration, and that's it. No little funky mathematical stuff with it. And then time is the x-axis, and it's a negative slope because of the negative k right there. Okay, so if you graphed it and it was really, really close to r squared being 1, it would be zero order overall. Or for that reactant, sorry. Oh, no, not that. Let me go down there. Okay. Here it is, someplace. Okay, so yet again, we're plugging in for a final, a naught over 2. It's just the half the concentration. So that's what I show here. Plug it in. When you solve, once you finally plug in a naught over 2 equals to negative kt plus a naught. How do you solve for t? Anybody?
Isolate.
Okay, so
Add the a naught to both sides and then divide by negative k.
so minus it and then divide by k. Yeah. Okay, so and I'm going to show you right here first. Let me go here first. Okay. So when you minus that a naught, think of it like this: 1/2 minus 1. 1/2 minus 1 is a negative 1/2, right? But then when you divide by negative k, a negative negates one another, and then you just have 1/2 a equals to delta t. I can find it down here. Equals to time, half-life. And sorry, the k is here as well because you're dividing by k, but I'm just trying to tell you it's a positive number, because time should never ever be negative. Time is always a positive quantity. So first order half-life equals 0.693 over k. Okay. Second order is this. Zero order. Look back. Oh no, I'm sorry. This is zero order. I did in another order, another sequence. First. Okay. Second order is concentration. Okay. So they're all different. You gotta know the differences. This is the only one that's a constant. Cool. And then I'll help you organize your notes a little bit because I have a graphic organizer for you to help with that. Okay, and then some of us, my first period, were telling me that they've already started deciding on what their topic was for the public service announcement versus us doing a lot before. I told you that little, just a poster. Pharmacology is really big in that because, like, Tylenol, why do you think they say on the bottle take every 4 to 6 hours? What happens after 6 hours?
It's dissolved.
It's not dissolved.
It's used up.
It's consumed. So yes, it has to dissolve to be consumed, but it's gone. Like the rate is probably, it's most likely, I don't know, it's just on the second order, it says it in here someplace. But every so much time it's gonna use half the reactants. And then after that, it's gonna get to be such a minuscule amount, it's gone. So no more pain relief, so then take more. Okay? So that's why, like, pharmacology is, you gotta know your kinetics to go into pharmacology. So that may be a good example to use. All right, let's do this one. I have another one just like this, and I'll do 2 more on the lecture notes, and I'll let you guys do your work. We have 45 minutes. Yay, this is on your packet.
It is?
Mm-hmm. So it's this,
Stapled one?
yeah, the big staple one. And then we're gonna work as one big team, since there's only 4, because I need...
No, once we finish this.
Okay, yeah, we're gonna work in a big team, because I need 3 calculators working to do all the 3 rates. So we're gonna work in a group of 4 here, okay? All right, so this is in your packet. Do you see it, Tyler? It would say like integrated rate law lecture notes or something like that. Just past the graph, lower left-hand corner.
Yeah.
Okay.
Rate law. Yeah.
All right, so what I'm giving you is data. That's it. You have to integrate it. So you have to graph it in accordance to first, second, and 0. All right, so I give you time, which is going on what axis? X-axis. And then this is going to be, if you just simply graph the concentration, what order are you doing? With your notes. If you graph the concentration of the y-axis. That was the 0 order one, right? Okay. So if you graph this one, it's 0 order. If you do, how can you manipulate this data to be first order?
Take the natural.
Right, L in that baby, okay? That's going to be first order. And then how do you make it second order? 1 over the concentration. So it gives you the concentration, you manipulate it as you put it into your stat plot. Do you understand? You can only do 1 order at a time. So 0 order, Shane, let's do first order, Lexi do first order, Tyler do second order. So we can all kind of team together and give me the R squared values. And yeah.
Wait, so you put this in your table?
Yeah, you put it in your table. You make sure your diagnostic is on. Huh?
Does it? I guess it's not gonna matter if it's in like degrees or radians, correct?
I don't think so. That's past my degree level.
No, we're not using
I'm just making sure.
Marco's teacher told me that his girlfriend's name was Sakatoa, and I believed him, and I was like, oh my gosh, he made up this rule in accordance with his girlfriend's name.
Oh my god.
I was very gullible back in the day. So yeah, you have to make sure your diagnostic is on so you get your R squared value.
Stat diagnostic.
Is this still recording?
Yeah, it's still recording. They can pause it. You guys can pause it and wait for the answer.
Oh, there's something that you did at the same time we had.
True that.
Okay.
Alright, so who's got 0 order? Ready?
Yeah, I would, but there's nothing on the graph.
Oh no, go to LinReg and do what is it LinReg?
Yeah.
And then
Look for the R squared.
yeah. Alright, hold on, let me write this up. 0 for a second. Before we even give me R squareds, what was the y-axis for 0? Anybody, what was the y-axis for 0?
The y-axis is concentration.
Uh-huh. And that's for time, right?
Mhm.
For first order it was
It's your LN.
uh-huh. I'm just making sure we know it, because the more we say it, the more we practice it. Yes, truly, because it'll become second nature as to what you're putting in your calculator. Okay?
It will always be time, right?
Yes, always integration with time. Okay. Alright, so the R squared for zero order was,
0.607.
okay, first order,
0.85.
and then second order,
0.365.
I think that's wrong. Let's recalculate. 0.999. So it could be a slip up in the calculator. Make sure you're putting 1 over the concentration of each of those. And you're looking at R squared, not R. So that's why I'm having everybody practice at least 1. You can double check that for me if you want to, but that's what I got when I did it. Okay, so looking at these, which is the most linear?
The second order.
Second order. Okay, now help me draw the graphs real fast. What does a zero order graph look like? Negative or positive slope? Negative. Is it linear? Not so much.
Should be, but it's not.
It's not for this data, so it kind of looks like that. So it's got a curve on it. That means it's not linear. I'm just showing you what the graphs would look like if you actually had graphs in front of you and not a calculator. All right. So first order, positive or negative slope? Negative, and it's almost linear. I mean, it's not bad. It's kind of like that, though. You did think. Okay, good. I just make sure you verify. I just have you guys verify. Yeah, I do that all the time. You gotta make sure you're not like club fingers. Okay, and then second order for positive or negative slope. Positive, and it's gonna be like it looks like a curve. It's straight line.
You're getting excited.
Yes. So if you had graphs to look at, you'd see these 3 graphs. You say, and it says what's the order. All you gotta do is say the one that's the straightest or most linear is the correct order. Therefore, it is second order. That's it. That's it. Just graph it, put it in your stat plot, figure out the R squared value, or literally look at graphs. We're literally going to look at graphs later, though. Okay. But now we have to get the value for K. How do you want to do that?
Go to it when time is 0.
I don't want to calculate it. Psh.
Oh,
The lazy way.
It's so slow.
It's the slope. Okay. So the slope of the second graph. So slope equals K on y equals x plus b. So whoever did second order, give me that slope. 10.16. And then now we have to figure out the units. Because K is not complete without units, right? Darn it. So tell me the units based on the rise over run.
Inverse of molarity and inverse of second.
Very good. So all you did was take rise, so 1 over, so 10.16, and then units for this is 1 over molarity, so molarity goes on bottom, and seconds are also on bottom, because run is the x-axis. Good job, guys. That is the K. And then I think there was, what's the half-life at the initial concentration? That's the last thing we need to do from this data. So knowing that this said it's a, I'm sorry, I just lied to you. Knowing that this is we just calculated as second order reaction, half-life for second order. So what's the formula for that?
Whatever K concentration is equal to T in half-life.
That?
Yeah.
All right. From the initial concentration, what's the initial concentration?
0.1.
0.1, right? So plug and chug. So T1 half is equal to 1 over the K we just calculated, 10.16 per molarity seconds, times concentration, which was 0.100 molar. That's well, that's not quite. I did 10 in first period, and I could do it in my head. I was surprised. So 10.16. What did you get?
0.984.
How did I know it's seconds?
Because it's per second.
Because what happens here?
They cancel.
Yeah, this is actually in a denominator, and this is kind of an enumerator of the denominator, so molarity is canceled, seconds, and we're doing time, right? 30 seconds. That'd be the only thing that relates to time. Cool? Alright, one more just like this, but you're calculating slightly different. Actually similar values, but you're given time, concentration. Let's do 0 second. Okay. Did I give you second? Oh, you had first.
You get first.
You had first.
Yeah.
I switched it up.
How do I know the diagnostic? Go.
And my video fans, you guys can pause and do this, or do this with us.
Okay, what am I doing?
You're doing second order.
No, I thought it was in first order.
Oh, I'm sorry. Sorry, you're doing first order. I should. Talk, I don't remember. I'm gonna fill out the charts just 'cause I like to graph stuff. Maybe. Zero. Whenever you're ready. Good.
0.97.
First order, people. Oh,
I got
or
second.
second order. Go for
I
it.
got 0.971.
Okay, so these are kind of close, right?
I got 0.972.
For second order? I mean, for first order?
First.
I did again.
I'm gonna override you real fast.
Okay, go for it.
Because I calculated I got 0.9999 to be specific. So even though they're all very, very close, the most linear would be first order, right? So it's going to be a first order reaction. Graph these again for me real fast. What's this, the zero order one look like?
Negative, kind of a curvy.
Not negative, kind of curvish, okay? First,
Linear.
negative or positive?
Positive.
Negative. Yeah. Straight down. Okay, and then second order?
Positive, kind of curvy.
Kind of curvish. Okay, so you could go from graphs and get the information or from data tables. So this is the most linear. Alright, so do me a favor. Let's write out the integrated rate law for first order. You can do it from your head or do it from your notes. Integrated rate law first order.
Concentration. No. Okay. Oh, one.
We just
I want
condensed version.
the concentration of a initial or
A
a final equals negative K T minus
No.
or plus concentration. Oh, never mind.
Good.
Yeah.
She's trying, but it's the first time you guys seen this, okay? I mean, you're gonna get to this point where you're like, telling them out. So make sure you get your elements. So I want you to determine K for the rate law. Can we do that easily though? True. Yeah. Let's just use slope first. So K is equal to the slope, which was what? Whoever did second order or first order.
Oh.
No, I did first order, but I messed it up.
I got you.
Yeah, I was
Negative
When you
point.
find the integrated rate law, you're integrating the differential.
You are integrating the differential.
Just like the K.
Yeah, but you have to have, two things equal to one another. So there's that graphical one where you have the change in concentration or change in time, and then actually what the differential is. All these things are actually equal to each other somehow. Okay. K is actually a negative. The K number looks negative here. Okay, but K is not a negative number. So I'll put a negative there to show you that the slope is equal to that. Okay, but what are the units for this?
Is it the same one that it was in the other one?
You look at the graph.
First would be first
Okay, why do you say per second?
because
Using the graph, not differential rate lines.
because it's a straight line, so
It actually has something to do with natural log. I'll show you. But if you can't get it from the graph and you're like, I have no idea how to use the natural logs, you can go back to your initial little rate is equal to K times concentration of whatever our reactant is, where if rate is molarity per second, what does K have to be if A is in molarity? That's how you do it in your head. You're like, oh, that's 1 over seconds, that's per second. But if you do it like, you rewrite this so you can actually maybe see it. Let me choose 2 points. let me choose 2 points. I'm going to choose these first 2 points. Okay? Put it in the integrated rate law. So time is 6.67 minutes. Oh, I'm sorry, this is not seconds, this is minutes. Because the graph is given, the table is given to us in minutes, so it's minutes. And then the molarity is 1.4 and then 1.1. Okay. So if you put in ln of the final, which in that case was 1.1.
1.4.
No, the A initial was 1.4.
Oh.
See, this is the initial, this is final. So 1.1 molarity. And I'm solving for K, so I'm going to minus this over here, right?
Mm-hmm.
So minus ln of 1.4 equals negative KT. What happens here? How can I condense this?
Divide.
Ln, now this is where I'm showing you the molarity part. 1.1 molar divided by that one, 1.4 molar. What happens to molarity? It cancels. That's why molarity is no longer in existence in our K. Okay? So that's how that works, and then you can solve for K. Or you can solve for T or K. K when T was 6.67 minutes.
Will always be just seconds.
Or just time.
This is first order.
For first order. Yep. And this is per minute just because the graph says so. Okay. Oh, half-life. It's not for half-life for this one. What's half-life equation? First order.
Oh, that's just the
9.3 over
Okay.
over what was it?
So K or
0.0361. And I'm going up here and I'm going to circle this. So don't forget that this is actually, the slope is negative, but this is actually a positive number.
is K
So is the equation with
K is positive. Yeah, and because down here, if you have a negative K, I mean, you're going to have a negative time, and that's stupid. You can't have a negative time. So I show it there, it's negative, but that's just representing the slope. So 0.0361, I think is what it was, per second. Nope, per minute. Anybody?
19
What's the minutes? That's because this minute actually comes up to the top when you do your flop thing. Copy dot flop, and then it's just the minutes.
I just say multiply by the reciprocal.
Thank you. Simplifies those fractions. Okay. I have, you guys are okay on this one? Can I go forward?
Yeah.
All right. Do you want to take a break for a second? You guys can, actually, I want to do this. Can I do this? I'm doing this, okay. First, this is the lecture ones. I'm going to do 3 on the lecture, and I'll let you start your homework, or maybe I'll just do 2. You haven't seen one that's given, like, absolutely no information, right? You only seen one of the big data tables. This has, like, minuscule information. So I'm going to show you how to do these. Okay. The first order decomposition of cyclobutane at 750 Kelvin is found that 25% of the sample has decomposed in 80 seconds. That's it. But I also know it's first order. So obviously I'm seeing time here, so I gotta have my integrated rate law. What's the integrated rate law for first order again?
The ln final concentration.
That CV is cyclobutane, okay?
Equals the negative KT plus the natural log of the initial concentration.
Good. I ask you a lot so you can keep saying it out loud and memorizing it. Okay. So I have information. The only piece I know for sure I have is 80 seconds as my time, right? I kind of have some other information. It's just not numbers. What's given?
5%.
Has decomposed, right? But I don't know initial and final.
Wait, but can't we
But
assume that 25 is in 80
one-
seconds, so 50% will be in 160 seconds, so that's the half-life?
Okay, so that's because you know half-life in first order. Can we just make it easy?
But you can do let's make the final 1/4 of the original or of the initial.
Minus 1/4 of it, right? Because it says it's found that 25% of the sample has decomposed.
Oh yeah, minus.
How about we just, what's the easiest
Or
number?
say 4.
1. Okay, so 1 is what we start with. What do we end with? 25% is decomposed. 3/4, 0.75. I know, I'm just making sure we're on the same page, okay? So, if my initial I like to make up easy numbers is 1 molar. My final has to be 0.75 molar. Okay, plug and chug. What are we solving for? K. All right, I don't want to plug it in yet. Actually, can we solve for K first and then plug it in? Because that makes your variables a little bit easier to work with. So ln of the concentration final minus ln of the concentration initial divided by negative t is what K is equal to. Just rearranging those algebraic terms there. I did that right. Yeah, okay. So this on the top though, I mean you can plug in your calculator just like that, or you can plug in your calculator as ln of the final, which was 0.75, divided by the ln of the initial, you know, you're dividing, so it's just 1 molar here, over negative 80 seconds. Molarities cancel. That helps you see that the K has no molarity. And tell me your value when you get there.
So we don't need the temperature at all.
No, temperature in this case is irrelevant, but it's a formality to say it because when we get to Arrhenius's law next week, temperature is important.
0.00360.
I believe you. I put my answers down some zeros. Say it again.
0.00360.
Yeah. And I got 359. I think I rounded to 360, so that's cool. Per second. Alright, that's okay. Alright, how do you get the half-life then?
It's
First order.
point
693.
693 over K, which is like 0.036.
Okay. See how, I mean, if you know your formulas or you have them accessible until you know them, you can totally do this. Just using the appropriate formulas and understanding what information the question is like mysteriously giving you. Like up there, we were trying to say, what do we plug in? So tell me what you get.
192 or 193.
Seconds. Cool. All right. Let me pick a slightly different one. Okay, we're gonna do 2 and then 5, and then I'm done. Thank you for bearing with me in my extra examples. All right, 2. The decomposition of hydrogen iodine formula for that. Hi. Okay. Is a second order. Half-life is 85 seconds when the initial concentration is 0.15. So this is all I'm given. Time, the order, and concentration initial. How do I get K?
You do the formula first and then solve for
This formula of what?
second order.
But see, I don't have enough information. So what's the second order what's the second order integrated? 1 over
1 over concentration. Final concentration
final,
equals negative K. Or
We can use
equals
the-
positive K.
I need this stuff, so I'm writing it down.
Or plus 1 over the
Concentration initial, right? I just like boxes like that, so just instead of putting stuff in there. Okay, so I could use that, but I only have initial, I don't have final, and I don't have K, so I can't use that one specifically. But it tells me half-life, so what's my half-life equation?
1 over K concentration or initial is equal to
The half-life? Alright, do I have everything there I need?
yes.
Yes. Okay, so plug it in. So 85 seconds equals 1 over K times 1.5 molar. Not 1.5, 0.15. How much you get? You can rearrange it.
Oh, yeah.
What'd you get?
That was fine. Okay. 0.07.
0.078, right. So essentially what you're doing is 85 times, I mean, if you multiply by everything by K and then time, or molarity, 85 times K times 0.15 molar is equal to 1, and then divide by 85 seconds. I'm just doing this for the benefit of anybody who needs this. K is equal to 0.078 units. Yeah, you could just flip on units for that.
Second inverse
Inverse molarity in seconds, right? And you can see that because I divided by molarity in seconds, so just in case you can't see it, it's right there. And then this is molarity to -1, seconds to -1. That is K. Okay. All right, next one. How long will it take for concentration of HI to go from 0.3 to 0.1? Plug it into that. So how long is I'm solving for time, and then I have my, what is this, final or initial?
Initial.
Initial and final. Plug it in because you have your K now, and then we can just solve for T. So one, and I'm going to rearrange this first. 1 over concentration, final, KT plus 1 for initial. And then I'm solving for T. So I'm going to do 1 over final minus 1 over initial divided by K to be T. So 1 over point 1 minus 1 over 0.3 over 0.078 molar seconds. What do you guys give me there? 85.03. I'm going to go 85 because of sig figs. Okay, 85 seconds. You guys are good at this stuff. Neat. I do have one more though, just so we can remember. How do you do inverse of, or how do you get rid of a natural log? E. Good. Just don't forget that. All right, I'm doing number 5. In the first order decomposition of acetone at 500 degrees C, it's found that concentration is 0.03 molar after 200 minutes. So that's our first bit of information. Like I'll give it to you in a data table, but I give it to you in a sense here. And 0.2 molar, not molar, after 400 minutes. Okay, so I'm not giving an initial concentration. I'm kind of giving a final, but at 2 different times. And I'm giving a time difference. So let's do, first of all, first order integrated rate log.
Ln of the final plus the natural log of the
And A is acetone for me. Okay. What kind of information do I have that I could put in here?
You have 2 points, can't put them in a calculator.
Okay, but what would my T be?
You could put the slope, just
Okay, but the slope, so there's only 2 data points, right? That's kind of weak to put in the stat plot and try to figure out. I mean, we know it's first order though, so technically we could do that. I'd be interested in to know if that gives you the same answer. Or we can plug in the information given.
Yeah.
But think of it this way, okay? So this information was the first information I knew. This is minutes here. So I'm going to call that I initial. Those are quotation marks. Wow, what's going on? Okay, I'm just going to pretend it's not there. Okay, and then this bit of information is the second information given to me, so I'm going to call that final. What is the change in time though, or the time that's elapsed from point A to point B? 200 minutes, because you're going from 200 minutes to 400 minutes, so we're going to call T 200 minutes. Really, I just wanted you to see that, because once you know your T, you can put that information in there. Okay, so then you're going to solve for what we solve for, K. So K is equal to ln of A final minus ln of A initial divided by negative T. Yes? Yes. So K is equal to ln of, what's our final concentration? 0.02 molar. And I'm going to go ahead and divide here because that's how logs work, right? So minus an ln of A initial will be divided by 0.03 molar divided by negative 200 minutes. What do you get?
0.002.
203. Because you need 3 sig figs because of all these little extra zeros that are here, and the 200 minutes is actually 2 sig figs because of the decimal point after the 2 minutes, or the 200 minutes and 400 minutes. You need 3 sig figs. I'm just want to get back into that because there's on your AP exam, there'll be one question that is entirely, I mean, it's a very, very qualitative. It's a lab-based question, and they said they would not give you credit unless your sig figs are right. If it's only for your final answer, like you'll get credit for your work, but if your final answer isn't right, 2 sig figs, then they won't give it to you. What's the units for this? Over minutes, because the malarity's canceled, right?
Attention teachers, students are getting out of the assembly in the auditorium, and they will be heading to second period at this time. Thank you.
Half-life, how do you get there?
Do you need to know teacher?
No.
Temperature is just miscellaneous for now.
Point, or, yeah, 693.
See, yours are pretty good. You don't have to look at your papers anymore. That's 341 minutes, by the way. I'm trying to finish this before they get in here and say they've been working the whole time. Okay. Oh, dang it, last one. What was the concentration to begin with? What do I know, and what can I solve for? What do I have to solve for? What's the question?
Can't we
We have to solve our concentration initial.
plug in .03
Uh-huh.
and 200?
So this would be labeled as what? Concentration final, and this would be T. Yep. Use that first point, plug it in, solve for initial.
Does it matter which one we do?
Usually no. You might get a slightly different numbers because of the linearity is not 100% linear. It's like 0.99. So I don't know why I like to keep writing this, but I really enjoy this. I have to write it again. I'm gonna solve for L and initial. Can you get that for me? Somebody think they're very excited. I'm videoing.
How'd you close the door?
Yeah, use this. Is that right? Yeah, that's right. So when you plug this in, Ellen, which is point. What? Open?
You're gonna say like
Wait,
point
wait, plus, what was our K value? 0.00203. Be quiet, we're videoing. Over minutes times 200 minutes. What do you guys get when you get there? Sorry, slow. I just rearranged it. You can-
There, negative
Yeah, give it to me.
-3.1.
So ln of concentration initial is equal to negative 3.10. Yeah? Alright, how do I get rid of ln now?
Put it to the E.
E to the ln is equal to what? Or the, oh, sorry. Hold on. So then solve for it that way.
0.0.
So concentration is equal to what?
0.045. I guess.
No way.
Came to say hi while we're going.
Well, I'm videoing right now. I'm videoing. Okay, that's it. Thank you, people who are here. People who are gone. You have to watch this video. Let me stop videoing for now.